Hello, my name is Esteban Mena. In this video, I will discuss my research in combining statistics and machine learning to analyze the student data from the University of Wyoming. When I started this project, I had two goals in mind. Could we find any strong correlations between a student's academic data and their success in college? And could we train a machine to categorize students based on their academic data? To begin, let's talk about the statistics of the project. When I saw the data, I decided to approach my interpretation of it by using regression analysis. This is the practice of using 2D and occasionally 3D data points and analyzing them to find correlations, patterns, and most importantly, trend lines. If a trend line exists, then so does a mathematical prediction equation, which can be very accurate if certain rules apply. I'll talk more about that later on in the video, but for now, let's start talking data. I received all my data from Dr. Craig Douglas in the math department, but at the same time, I requested additional data from the university database. This is everything I was hoping to work with. My goal was to use GPA as a measurement for success. The rest of this data would be used to categorize students into groups if there seemed to be any strong indicator for uniqueness. For example, would students in a specific major have better starting GPAs as compared to other majors, and etc. Unfortunately, after weeks of waiting, this was all I had to work with, though I'm not complaining. It wasn't what I was hoping to be limited to, but it's still a lot of data. Since high school GPA, first term GPA, and final GPA were the only three numerical data I could use, I revolved my analysis around them. In the end, I was still able to work with the data of almost 65,000 students. Let's take a look at my results from comparing students' UW GPA to their high school GPA. From the plot on the left, we can see that the data points are all bunched up into the top right corner with a large amount of students sitting at a high school GPA of 0. The residual plots on the right also look like they are skewed and clustering where they shouldn't. When plotting a trend line, it resulted in a prediction equation of 3.291 plus 0.025 times high school GPA. This is much too flat to be trustworthy, and I think I know what the problem is. Most likely, students who don't have a high school GPA recorded are defaulted to 0, which pushes the y-intercept of our equation much higher than it should be. Let's remove these points and see what happens. There we go, much better. But I don't think it's enough to make reliable assumptions. Remember the first rule of plot analysis. If it's easier to find a star constellation than a trend line, then chances are there isn't a reliable one. But take a look at our residual plots on the right again. They look very good for some reason. In residual versus fitted, the data points look to be properly distributed, and in the normal QQ plot, it looks like the residual points follow the trend line very well. This honestly can mean two things. Either this is a classic case of a coincidence, or it could be that if I limited my data to specific high schools, the trend line would become much clearer. But due to time constraints, I didn't have time to do this, so let's move on to our next example. UW GPA versus first term GPA actually came out really well. Just by looking at the plot, you can tell that a trend line already exists, and no additional limiting is really needed. The equation we get from the trend line is 1.458 plus 0.576 times the first term GPA, which is reliable. The residuals on the residual versus fitted plot are pretty evenly distributed, which is good. That means that there is variation in our data. And on the normal QQ plot, the residuals line up very well with the trend line, with no outliers. I won't go into too much detail about this slide. I mainly wanted to show you what I mean by limiting the data. In this case, I separated UW GPA versus first term GPA into different colleges on campus. As you can see, each plot has a slightly different trend line, which could be used for further study. Okay, now that we're done talking about the statistics of the project, let's start talking about machine learning. For this project, I wanted to see if I could train a machine to accurately categorize students into different clusters based on their academic data. I decided to implement the kth nearest neighbor algorithm. The way the kth nearest neighbor algorithm works is actually very simple. Let's say we have a set of data points on a 2D plot. They each have an x value and a y value. The only thing that separates them is their color. Some are blue, some are yellow. Now let's add a new uncategorized data point. Using the kth nearest neighbor algorithm, we look at the kth nearest neighbors, see how they are categorized, average the results, and then categorize the data point. Since the nearest neighbors were all yellow, the new data point is categorized as yellow. When I tested my data, I used students' high school GPAs and their UW GPAs to categorize them by the combination of their letter grades. GPAs above a 3.0 were considered an A, 2 and above were a B, and anything below was a C. So there was a total of 9 different categories that each student could be classified under. The program randomly selects about 2/3 of the students to use as training data. The rest it uses as testing data to see just how accurate the computer can categorize the students. As shown in these results, the computer predicts the category of each student with about 90% accuracy. The application of this is if we added more columns of data that are used to categorize a student, then there is more information the computer can use to categorize the students. For instance, say we add AP test scores as new data. Judging by how the machine categorizes a student, we could use the results to better plan a new student's college path. With that, I hope you enjoyed watching this. Thank you, and goodbye.